Hello, in this tutorial I will show you how to use machine learning MACE foundation model with genetic algorithm to find most energetically favorable distribution of certain substitute or vacancies point defects in a crystal structure and in interactive streamlit application. And this application is available on my GitHub link. So if you go to this site, you can find a tutorial how to compile the application, and also there are 2 YouTube videos which show the compilation as well, and they illustrate how to use this app to calculate, for instance, just a single point energies or geometry optimization, elastic properties, or phonons. And videos are available at the implant group team, and it's these two, where this first one shows how to perform the calculations directly in this interface, and the other one is how to generate a Python code in this application that you can copy into the console and run the simulations directly from the console with the settings that you will change here. Okay, so here I want to just focus on the application of finding the lowest energy candidate for the lowest energetic state of distribution of point defects in a crystal structure. And as an example, let's say I have here the alpha titanium structure, and I want to create a supercell 3 times 3 times 2, and placed in it 16% of nitrogen substitutions. And yeah, I don't know at which positions I should place them. Should I do it randomly? But then I don't know if the energetic state will be likely the lowest one or not, and I would like to create such a lower energetic state that I can use, for instance, to perform some advanced simulations with DFT. Okay, and one of the method how to find such candidate is to use this universal machine learning MACE model with a genetic algorithm. So let's start with it. I need to first upload this structure into the application. So I have here a zip file which I copy here. Then I need to accept it and log the structures. After that, I can change which MACE foundation model to use. So to have the calculations finish as quickly as possible, I will use this smallest model, and I can then select how many CPU threads I want to use for the simulation, or if I want to use GPU. So I will use GPU, which is much faster, and my GPU is just RTX 2060 Super. And then I have to go to the calculation setup and select this genetic algorithm structure optimization. And if I already uploaded some supercell, I can just confirm it, or I can define the supercell directly here. And let's say I want 3 times 3 times 2. So total it will have 36 atoms, and it allows me to have almost 3% steps with the substitutes. So now I need to confirm the structure, and once I confirm it, I can modify which atom types to substitute, and with what atom, what element, or and at what concentration. So I can either choose vacancy, or any element. Let's do nitrogen, and let's do just this 17%. So in the final structure I will have 6 atoms of nitrogen and 30 remaining atoms of titanium. This is the settings for the output structure. And now I have to set also the parameters of the genetic algorithm. So here it's the population size, so the total number of structures in each generation, then the maximum number of generations. So to be quickly done with the calculations for the illustration, I will reduce it to like 15 and the maximum generations like 10. And then I have here a parameter which says how many independent genetic algorithm I want to run with different initial seeds. So this will run the genetic algorithm 3 times always, and the initial population will be generated randomly in a different way. Then I can set the how many percentage of the best structures from the previous generation I want to move to the new generation, so like 10%. And then the mutation rate, so what is the probability of each gene of the child to mutate the gene, and the crossover rate, which means that there is an 80% probability that the child can inherit from a pool gene from both parents, from all gene from both parents. Or I have an example here actually. So yeah, here. So let's say that the first parent has these 3 genes, which are the substitute sites, and the parent 2 has these additional 3 genes, so 3 substitution sites for silver, and there is the 80% chance that the child can inherit from all these 2 pools the genes, and then like because it must have just 3 genes, 3 substitute atoms, these 3 will be randomly selected from this gene pool. Or there is 20% chance that the child will just inherit all genes from either one of these, one of its two parent, which will be chosen randomly. So for instance, it can happen that the child will inherit all genes from the parent number 1, all these. Okay, and yeah, then I can choose that if I want to, before calculating the total energy of the structure or the habitat in that generation, I can perform first optimization of the atomic positions. So here I can set certain parameters of this geometry optimization, but to be quicker with the simulations now, I will not use this option. Okay, so all parameters are set, and now I can run the simulations. So for that I have to go to this tab, Start Calculations, and then Start Batch Calculation. And now I can move to the calculation console, where I can see like which current genetic algorithm run is being calculated, which generation is being calculated, and rough estimation of the remaining total calculation time. So let's wait a little bit. It will finish quickly, and once it will finish, then I can go to this result section and I can see the results here. Okay, and now it's done. So we can go to the results and then to the genetic algorithm, and I can find here like overview of each of the independent tree runs and compare the best structure with the lowest energy state. Then I can select just one of the three possible genetic algorithm runs and see like what was in the current generation, what was the best energy or the structure with the best energy, what was the average energy in this generation, and what was the worst energy. And I can also see the convergence, so the best energy in each generation for all three independent kinetic algorithm runs. So in this case, I see that it likely didn't find the minimum, as these two has higher energies than this one. So probably I would need to increase the population size or the number of generations. And then for further simulations, like in VASP, for example, I can download the postcard format of the best structure from like all these three runs. So it will download the structure which has this energy, or I can download like let's say 50% from the last generation, 50% of the best structures from the last generation for certain selected genetic algorithm run, or I can download in batch all the best structure for each of these three independent runs. So like this structure, and this structure. And just to illustrate you, I will download this one, save, upload it to Ovito. So you can see it's like the supercell of alpha titanium with 17% of nitrogen, and it is a likely candidate which leads to the minimization, which has the minimum energetic state as predicted by this MACE, universal MACE machine learning foundation model. Okay, so one option is to run directly this genetic algorithm in this interface, and the second option is to generate a Python script. So I don't need to change anything, just I need to go to the start calculations and click on this generate Python script. And this is better to do if you plan to run certain calculations which are expected to take hours or days to finish. So to have more stability, it's better to run it in a separated console than in this web-based application. And it's very simple. You will just copy, or you can download the script. So I will copy it. Then I will go to my console, and I need to make sure that I will activate the virtual Python environment with packages that are the same as the ones installed for this application. So first I will activate this virtual environment. So I need to go to where I compile this application, software, MACE, and now I will activate virtual environment. Okay, it's done, and I can go back to this test folder. And here I have just like these two structures for illustration. So like the alpha titanium with which is the unit cell with 2 atoms. I can make a new directory. Let's call it test1. So now it's completely empty, and here I will copy this script. So I already copied with this button, and now I will create a Python script, insert the content, save it with Ctrl S and close it with Ctrl X, and I can run it now. So Python 3 run, and it will do the same as what was done in this upstreamed application, and it will automatically, it also automatically created this supercell. Okay, so I created there is a little bug. It took this structure which was already supercell as the initial one, and it created a new supercell from this like 3 times 3 times 2, but never mind, now I will fix it and it will work correctly once you will try it. And yeah, it's running basically the same. Actually, just to be quicker, let me reset it completely, generate it again. Let's generate it again. So I uploaded the structure, and I will create the supercell, and now I will set here like, I don't know, let's say 2010. Yeah, I need to select the elements. Okay, so that's all, and I can generate a Python script again. Oh, here I need to change also. Copy. I will delete everything. Create this Python script as a new one, and now let's run it. So now it should be the correct supercell. Yes, so initial one was this structure with 2 atoms, and now the supercell has 36 atoms. And yep, it's performing the same run, and you can see like the best energy in the current generation, average energy, and worst energy, the energy range improvement compared to this zeroed generation, and estimated remaining time. So now it went to genetic algorithm run 2 and run 3, and all the results are automatically saved. So if I show you test 1 genetic algorithm results, I have here like this graph showing the best energy for each run, then convergence with generation for the best run, or no, yeah, this one. So convergence, genetic algorithm convergence for all runs, and I have here the best structure for each run, and also like I can download the the best 20% of structures from the last generation from each run. Yeah, so if I just, and these are, one is different energetically, so if I show you, you can see 2 are the same, but 1 is different. And now I have a likely candidate which has probably the lowest energy state for this distribution of point effects, and I can just if I want to be really sure, I would need to perform like DFT simulations, or also allow the optimization of atomic positions, and then I can run with this structure like in other simulations whatever I want. Okay, so I believe that is all. How to use this application to use genetic algorithm with MACE machine learning interatomic potential to find a likely candidate which has the lowest energy for certain distributions of substitute or vacancies point defects. And thank you for your attention, and I hope this tool will be useful for your applications.